can't get an intersection in the first quadrant. And in fact, if we draw the isoclines, you'll see that if I continued with these isoclines, you'd get an intersecting over here where x is positive and y is negative. And if you draw your arrows, what you'll show is that both grow in this region. Once they cross this isocline, where only y is growing and x is not growing, they go vertically, then over here, what is happening is y is growing and x is declining. And over here, what happens is they both decline until it crosses here horizontally. And so all solutions seem to go towards the y-axis, towards the isolation equilibrium for y. So in this case, you'll say that coexistence is possible. In this case, you'll say y always wins. Okay? And then, if we take the case where both alpha and beta are positive, this is this case over here, and I can even make this a little bigger, then you'll see that here are the isolation equilibria, here's the coexistence equilibrium, and here's the trivial equilibrium. If you start out, however, the solutions appear to go like this. So if you're in this section over here, what's happening is x is growing and y is declining. So instead of going in this way, which would mean that x would have to be growing, y would have to be growing and x declining, instead, in this region, you have x growing and y declining, and so the solution heads to here, and the other solution heads to here. And over here, it seems like you're growing towards it, but once you cross this blue line, you head down there, and you cross the blue line, and you head in there. So in this case, you initially seem like you're heading towards this coexistence equilibrium, but as you get near it, you either part in one direction or the other. Yeah. Right, so in this case, this equilibrium corresponds to y equals 1 and x equals 0. That's why it's on the axis. It's on the axis where x is 0 and y is 1. Remember, for this example, we said x and k and s equal to 1, and then we played around with different values of alpha and beta. And so we got these three different cases. In this case, no matter where you start in the whole plane, if you trace these arrows, now what you can do is you can take an over program, and you can choose this value of alpha and beta, and you can start anywhere, and you can see what the solution does. And no matter where you start, so the thing about a diagram like this is that you don't need to test initial conditions, because you say what happens in these regions. If you go straight to numerically to a nova program, you're not aware of those regions. And so you just start at different initial conditions, and you keep going to y equal to 1 and x equal to 0, and you're not quite sure why. What this diagram does is makes clear why y always wins. What happens here is that there's kind of a line over here. This is not a straight line. It looks straight. The equation for this line is very difficult to get. But if you start one side of the line, you'll end up at this point over here. If you start the other side of the line, you'll end up at that point. So this line over here that goes from this equilibrium to this equilibrium and out to infinity, if you start anywhere to the left of them, you'll land up at the isolation equilibrium where x wins. And if you start anywhere to that side, that depends whether left, right, or left, right. Anywhere to that side, then you'll end up with y. So if you start out where y has a slight advantage in that it's this side of the line rather than that side, it'll win, and x will win if you start the other side of that line. Yeah. Okay, that's a very good question. If you start exactly on the line, you'll head along the line to this point. You'll never reach it. You'll go applied asymptotically. There's one single point. So it's like, if something's unstable, I'm on a hill like this, and there's one single point where you can just sit. If you've got a saddle, you can imagine that on the saddle you can place a ball that will go back and forth on that line. But you just shift it to the left or right, and it'll either fall off that side or fall down that side. So it's kind of like a singular line. So the fact that a singular line is what mathematicians say of measure 0 compared to all the places you could stay. So a point has no length, and a line has no area. So you can take any patch of area over here and say, if I stay in any patch of area here, I'll end up there, or any patch of area here, I'll end up there. But a line has no area, so it's kind of a singular place. And any small perturbation will take you to one side of the line or the other. So nothing's ever that precise in nature. So in nature, it would be like balancing on the edge. If you took a ruler and put it vertically, at some point it's going to fall over one way or another. And so in a system like this, for which you have a model, something's going to be a small perturbation that's not accounted for in the basic equations is going to have a small effect to take it to one side or another, and then the dominant process, as represented by the equations, will then say that if you fall off on one side, you'll end up here. If you fall off on the other, you'll end up there. So, but mathematically, that's an idealized situation that will not arise in general. Okay, so that's a good question. And so the final outcome depends on the initial conditions. So somebody can be so who's the superior competitor in this case? In this case, the superior competitor is in the context of where you start out. And so you can imagine that implicitly somebody might be superior in the sense that the area on this side of the line is bigger than the area on the other side of the line. So there are more places you can start out where one wins than with the other. But in the end, the context is where you start out. Okay. So now when biologists say, okay, we have this notion that there's stable coexistence, or there's a dominant competitor, or here there's competitive exclusion. Now, there's competitive exclusion here, but one always wins. Here the competitive exclusion depends on the initial conditions. So when these ideas were known, that's when a Russian biologist, Georgy Gauss, set out a famous set of experiments in order to demonstrate competitive exclusion. And when biologists try to do experiments, of course, to do experiments on long-lived large animals, you need a lot of space, a lot of money, and a lot of time. So the easiest thing to do is to set up microcosms and do experiments on small things that have very fast generations where things happen fast. And in genetics, it so happens that the fruit fly turned out to be an incredible animal model for studying genetic processes because you could keep them in cages in the lab. There were lots of mutations that arose. They had short generation times. You could breed hundreds of generations in a few years and so on. And so what Gauss did is he said, okay, there's these two species of paramecium, and I can grow them in little containers. And what I'm going to do is I'm going to see what happens if I try to grow them together versus if I grow them separately. So what he did, and this is reported in a journal called Biometrica. So this is actually was reported by another scientist, Leslie, in 1957, who was reviewing these experiments. So that's what this reference is. But the earlier places where this stuff was published that are not quite as accessible as this 1957 reference. But what happened is that grown in isolation, you see a typical logistic growth curve. And then, when he grew the species together, you got this incredible result. So these are real data of both species seem to be doing okay, but then they diverge. They seem to be going towards the coexistence. So they're heading up towards the coexistence, but the coexistence is a saddle. And then they fall off to one side, and the side they fall off to is that the one species, Aurelia, wins and Caudatum loses. So I guess the biologists felt pretty pleased about the model and said this seems to be a reasonable model, at least for this particular species. So what you can do is that instead of using specific values for alpha and beta, you can examine what happens using inequalities. So if we go back to the original model that we set up, you can say, okay, what happens if alpha k is greater than s and alpha beta is greater than 1 and beta s is greater than k? And this is positive and this is positive. Or what happens if alpha k is less than s, beta s is less than k, and this is less than 1? And this is also positive or negative. Or what happens when alpha, so you get these 4 different cases that you can set up and you can study. And it turns out that there are actually 3 canonical cases, and 2 of the cases, so for the case where they don't intersect, there's only one case, not 2 cases, because if you change the name of x and y, you get the second case. So in one case, x wins, and in the other case, y wins. But if you change the name of x and y, it's really the same case. So you can set up these 3 cases, and you can read the general notes. Now, the first case, if alpha beta times k is less than beta times s is less than k, then it means that here's s and here's k and here's your carrying capacity. If you look where k intersects on this axis, and where this line here intersects on this axis, if k upon beta is bigger than s, and s upon alpha is bigger than k, then this drawing will arise. And that one leads to stable coexistence. And what happens is if you connect k and s with a line, this equilibrium lies above the line. In other words, the coexistence equilibrium says that there's some kind of competition that's not too intense. If there was no effect on competition at all, then your equilibrium would be over here. Because if x and y were not competing with one another, they would go to the point ks, which is over here. In the absence of each other, they go to k or s. If they don't affect one another, then they would end up here on this diagram. But they end up over here, but it's above this line. So we think of this as competition, but the competition is not as intense enough to drive this point below the line. Now we go to the case where instead of S alpha being above k, it's below k. And instead of k upon beta being above s, it's below s. And if we do that, we'll see what happens. So now if we join the points k and s, we see that these isoclines intersect and the coexistence is below this line. So it represents more intense competition. And when you get more intense competition, you get the situation where either one wins or the other, but it depends on the initial condition. And so either S wins or K wins, depending where you start out. And then the third case that arises, where one of these is bigger than S, and the other one is less than K. Then they don't intersect here. And as I said, that's the same as saying, if S were bigger than this, and this were bigger than that, then this line would lie above it. So, but what happens is they don't intersect. So this is one case. Because I can interchange the names of X and Y, and I always get this case. So there's a very famous ecologist, Francis Ayala. Anybody, you know that name because he's written some books. And what he said is, he did an experiment, and then he wrote a paper called The Invalidation of the Principle of Competitive Exclusion. And he published this in Nature. So Nature and Science are the most preeminent scientific journals in the world. They're the most preeminent because everybody tries to get their stuff published in these journals. Because these are the journals that science journalists look at and that non-scientists look at, and they expect to see the most important results there. So it's like the Super Bowl of scientific journals. And people pay attention to what's in this journal. When anybody publishes, usually if you submit a paper to a journal, Science or Nature, they won't even review it. Maybe 10% of the papers. So firstly, most people don't send their stuff there because they know it's going to get rejected. Secondly, if you think you've got something that's of general interest and good enough for these journals, you'll send it there, and 9 out of 10 times they'll send it back and say we're not reviewing it. Then 1 out of 10 times they'll review it, and maybe 30% of that they'll publish it or not, and 70% they'll decide that it's not watertight enough to publish. But when you publish there, you try to have a dramatic statement. So the Lotka-Volterra model, as encapsulated in these 3 different cases that we've looked at, that the first one where you get a stable coexistence, the second one where you get competitive exclusion depending on the initial conditions, and the third where you get what you might call complete dominance. This was called the competitive exclusion principle, but the principle itself is broader than a particular model. So the principle itself is a statement that's independent of a model. And the principle goes something like this. When 2 individuals are very similar, then the one who's slightly superior will win. In other words, if you want to reduce competition, you have to become sufficiently dissimilar so that the alpha and beta that we're talking about there are not close to 1, but are less than 1, and are substantially less than 1. Then what it means is that you're each partitioning out what's called your niche. So for example, if you come to birds competing for seeds, what evolution does is it takes individuals that are very similar, and it selects the one that's superior, the superior type. But if they're sufficiently dissimilar, then they can coexist. So usually what happens is that evolution will work on two groups of individuals that are similar. And what happens is those individuals who live at the end of the similarity spectrum, the one is the largest of the one type, and the other is the smallest of the other type, they're usually the fittest within those two because they're having the least competition, because they're kind of, if you're the largest of one type, you have less competition from the smaller ones because you have a superior ability, for example, to crack nuts, big nuts, and the smaller ones then have a superior ability to go around and pick up little seeds. And so usually the fittest individuals are the ones that are at the extreme of these two competing spectrums. And so the spectrums diverge. And eventually they diverge to the point where the alpha and beta for the two species is sufficiently small that they can both coexist under reasonable circumstances, even though there'll be fluctuations from year to year in the amount of seeds of the different sizes. And the two biologists at Princeton who studied very intensively what are called Darwin's finches on the Galapagos, and they've shown that from year to year, as different plants do better because it's a wetter year or a drier year, and the seed distributions change, so the finch populations, in terms of beak sizes of the different competing types, they also move around their spectrum. So you see actually evolution at a micro level in action on the basis of a couple of years, changes. And they've been studying these finches for 30, 40 years. Now what Ayala did is he made this very dramatic title, Invalidation of the Principle of Competitive Exclusion. That way he could be sure that journalists would be interested in it, the general public would be interested in it. And what he claimed is that, well, what he did is he took two species of Drosophila and he reared them in cages. And he had a look at the carrying capacities that they rose to. So he would go in every day and he would refresh the resources in the cage. And I don't remember what resources he used, but it may have been some kind of sugar water or something. And then what he did is he took both species together, he put them in this cage, and he said, okay, let me see if I can make this a little bigger because it's a little hard to see on the board. Okay. So he's got a species P and W, and he's got numbers. And when he takes under these controlled situation and he lets the P's develop in this cage, eventually the population reaches an equilibrium of around 750 individuals. When he does the same with this other species, eventually the population settles out at 1,200 individuals. When he puts the two together, he shows that he gets some coexistence. It's not very clean, but it's basically around over here, which lies below that line joining the two equilibria. So according to the theory, the competition should be intense enough that one should win. So this is the situation where the model predicts that there should be competitive exclusion of one by the other, and yet they coexist. So he made this dramatic hoopla about it. But he didn't really reject the competitive exclusion principle. What he rejected was that simple model, which we call the Gauss-Volterra model, as a model for competition. You can make another model for competition that predicts that the coexistence equilibrium can lie below the line joining the isolation equilibria, and yet it could be stable. So how could you do this? So an alternative model is something like this. We can say, okay, we have logistic growth, but the carrying capacity somehow depends on Y as well. So the carrying capacity always depends on your environment. You're a set of individuals, and you're a population, and your carrying capacity depends on your environment. Now, if I take Y and I add it to your environment, you can say, what's happening is that competition is subtle. It's not direct. It's not about directly affecting the growth rate, but somehow affecting the environment. So the environment may become smaller because individuals are staking out territories in some way, and they're preventing other individuals from exploiting particular areas. So if that's the case, you could say, what happens if this environment, in the absence of the competitor, is S, but in the presence of the competitor, declines? So this is like a function that declines hyperbolically. And the same for X. And if you do that, and you draw the isoclines, then you'll get a model that looks like this. So these are the S of X and the K of Y. And what happens is that instead of these being straight lines, the isoclines being lines, they're hyperbole. And then you can get an intersection below this line, but it can be, if you plot these, it can be a stable coexistence. So now you have another model. So what does this tell you? Well, it tells you that maybe for the plasmodium that we saw, when they competed with one another, they followed a Lotka-Volterra model, which means they compete directly with one another, but they somehow partition resources in their competition. So it's as though they're competing with themselves, but if the individual's slightly bigger than they are of the one type, then they're more efficient than